Algebraic symbols act as executable code, precise instructions for generating specific shapes in space. Adding a second variable expands this into a two-dimensional grid. The equation x squared minus 4x plus y squared equals -3 loops the line segment into a perfect circle. Calculus relies on this exact relationship between syntax and shape, using algebraic rules to rigidly define the boundaries of the coordinate plane. This environment is the Cartesian coordinate system, named for the 17th century philosopher René Descartes. It acts as the fundamental map where numbers dictate physical locations. The concept of distance bridges the algebra on the page and the geometry on this map. Calculus tracks continuous movement and change. Plotting that movement requires a mathematically defined architecture of distance. This number line shows absolute value as a rigid measuring bracket. It represents the non-negative distance from 0 to x on the real line. We can detach that bracket from 0 to represent the physical distance between any two variables on the line, x and y, as the absolute value of x minus y. Placing this distance inside an inequality, like 3x minus 2 is less than or equal to 1, sets a geometric constraint. As the variables are isolated algebraically, the bracket physically squeezes down to a specific bounded region, the closed interval from 1/3 to 1. These one-dimensional inequalities act as geometric fences. They create the bounded domains where the limits and functions of calculus will eventually operate. Mapping complex paths requires a second perpendicular number line, creating a two-dimensional space. On this grid, movement between 2 points, P1 and P2, breaks down into two separate increments, a horizontal distance, delta x, and a vertical distance, delta y. The Pythagorean theorem calculates the direct distance between these coordinates, yielding the formula d equals the square root of the horizontal increment squared plus the vertical increment squared. Dividing the vertical rise by the horizontal run gives us the slope. Setting that ratio as a constant generates a linear equation, y equals mx plus b. Straight lines are continuous chains of points locked into a constant proportional distance between their coordinates. This diagram shows how distance constraints generate nonlinear shapes. Anchoring a center point, C, and locking the distance to a constant radius, A, traces a complete circle. The squared Pythagorean distance formula from the previous scene produces the standard equation of a circle. In calculus, quadratic equations rarely arrive neatly organized in this standard form. This equation contains raw quadratic terms. We use a technique called completing the square to group the x and y variables, translating this string of characters back into a readable spatial format. Completing the square isolates the horizontal and vertical shifts. The equation resolves into x minus 2 squared plus y plus 3 squared equals 16, which centers the circle at 2, -3, with a physical radius of 4. Replacing the equal sign with a less than or equal to sign transforms the hollow perimeter into a solid disk, capturing points within that threshold. Completing the square locates and sizes shapes within the coordinate system. While a single distance constraint creates a circle, balancing two distance constraints creates a parabola. The parabola is defined by a fixed point, the focus, and a fixed horizontal line, the directrix. If we move point P so that its distance to the focus perfectly matches its vertical distance to the directrix, the point traces a perfect upward opening parabola. Equating the distance formulas for both paths simplifies algebraically into the standard equation x squared equals 4py. Because every point on this curve maintains that geometric balance, parallel signals striking the interior of the parabola reflect exactly to the focus. Radio telescopes use this property to concentrate faint signals from space. The parabola demonstrates how imposing precise distance rules generates the continuous, nonlinear curves that calculus is designed to measure. This grid pairs each establishing geometry with its defining algebraic syntax, the bounded interval, the straight line, the shifted circle, and the parabola. Modifying these distance constraints, either by scaling the axes unequally or subtracting the terms, generates the ellipse and the hyperbola. Intervals isolate regions, lines establish constant rates, and quadratics map continuous paths via distance. This coordinate architecture provides the setting to track infinitesimal change, compute limits, and calculate the exact area under a curve. Mastering these geometric translations provides the necessary framework for the study. If you had to describe a shape so precisely that anyone in the universe could recreate it blind, how would you do it? Our primary canvas is the Cartesian plane. We anchor a center point at 0, 0 and extend a rigid radius of 2 units. To describe the space inside, we use inequalities. Stating the radius is less than 2 fills the interior, cleanly separating it from the blank exterior. Mathematical equations and inequalities are our earliest tools for taking abstract, infinite space and trapping it within defined, controllable boundaries. This graph shows a different set of starting parameters on an open plane. We drop a single point, the focus, and draw a flat baseline across the bottom, the directrix. Plotting every coordinate that stays the exact same distance from both that suspended dot and the flat line below forms a distinct shape. That resulting curve is called the parabola. This parabola is a static collection of points. But describing a moving world requires a way to link variables together, turning geometry into a predictable system of inputs and outputs. Enter the function, written as y equals f of x. Think of it as a strict industrial machine. It takes raw material, applies a specific set of rules, and dispenses a guaranteed result. That raw input material is the domain. There is a strict rule called the domain convention. The machine breaks if fed invalid inputs, like dividing by 0. The finalized output, the numbers dispensed after the machine squares or multiplies the input, is called the range. This animated scatterplot shows how graphing works. It's simply plotting a chronological record of the machine's inputs and outputs. The data points drop into place, one by one, until they connect into the sweeping curve of y equals x squared. Functions translate invisible cause and effect into a predictive visual path on our canvas. Tweak the equation by adding 1, and the entire curve physically elevates. Subtract 1 directly from the x variable, and the graph slides horizontally. Certain formulas create even functions. Fold the plane in half vertically, and both sides of the curve align and overlap perfectly. Odd functions contain different geometry, featuring rotational symmetry across the origin. Make the function negative, and the curve flips upside down, rendering a mirrored reflection below the horizontal line. By editing these formulas, we shift positions and reflect paths to match any geometric pattern. What happens when we take these dynamic function machines and apply them to the simple circle from our first canvas? This diagram illustrates the unit circle. It operates under a highly specialized constraint. It is permanently locked to a radius of exactly 1. To calculate true mathematical rotation, we discard degrees entirely. We use radians. A radian is a measure of physical distance walked along the outside edge of the circle, a concept known as arc length. The unit circle traps a straight, linear measurement into a continuous, infinite loop. Looking at this animation, we track a single point traveling constantly around the edge of our unit circle. As it moves, its location gives us the core definition of trigonometry. The horizontal x-coordinate is its cosine, and the vertical y-coordinate is its sine. Because it orbits forever, we drag those sine values outward horizontally, sketching a continuous wave across time. Zoom back into the circle itself, and a hidden right-angled triangle maps precisely to the foundational rules of sine, opposite, and hypotenuse. These localized rules step off the Cartesian canvas to solve physical problems. By tracking the angles of elevation from 2 ground observers, we can calculate the exact height of a weather balloon suspended in the sky. From the rotation of a circle to the pulse of a wave, these functions bridge the gap between abstract angles and physical distances. They give us the tools to calculate what we